Welcome back to Developers Toolbox. Today we are starting a new series. The series of talks is going to be about kind of how computers work and how they think, so to speak. And for today, this first part, we're just going to be covering some baseline concepts that are necessary to understand that. So we're going to be talking today about numbering systems. So off we go back to kindergarten to learn how to count again. But we are going to learn to count using some different numbering systems, and we're going to learn about converting between those systems. We're going to learn about some binary arithmetic. So it should be good. Just kind of starting off, some different numbering systems that you may or may not be aware of. Decimal is the numbering system that we use on a daily basis for pretty much everything. It's a base 10 numbering system, which means there are for each digit there are 10 unique values, 0 through 9. So in addition to decimal, there's also some other systems that you may have heard of. Binary, or base 2, has two potential values for each digit, a 0 and a 1, and this is kind of the baseline language of digital logic and computers, and we'll be talking a lot today about binary. Octal is base 8 with values 0 through 7. We won't actually be talking a lot about octal today. There's places where it's used, but yeah, it's just a little bit off topic for what we're going to be covering, so we'll be leaving octal kind of off the table, but be aware that there is a base 8 system that exists. And hexadecimal, which is base 16 with values 0 through F. So hexadecimal, binary, both used pretty extensively in lots of things computer related. So we're going to learn about these numbering systems and how they work and why they exist and what their purpose is. So let's start off with why they exist. In digital electronics and in computers, there's kind of a fundamental component that makes up pretty much anything where there's kind of pathing and decision making involved. And this is a physical component called a transistor. You may have heard of these before. They look something like this, and you can see the diagram of what they look like. This is basically it has some interesting properties, but the most important concept to understand here is that a transistor has a typical transistor has an emitter, a collector, and a base. And whenever you apply current to the base of the transistor, depending on which type of transistor it is, you'll have current flow either from the collector to the emitter or vice versa, from the emitter to the collector. So the cool thing about this is it basically acts like an electronic switch by changing the value of what we're applying to base opens a pathway, and so this is basically, and there's some different types of integrated circuit packaging for digital electronics, being like TTL, transistor to transistor logic, and CMOS. And really the big differences between those is the amount of or the difference of potential, the voltage that's required to actually trigger the switch to open or close. But this is basically where binary comes from and why it's so important to understand within the realm of digital electronics and computers, because these electronic switches they basically make up everything, and they give you the capability to track something as either a 0, being that the switch is off, or a 1, being that it's on. So let's go ahead, ignoring all the stuff that's going on here physically. The important takeaway here is that you have these digital switches, and there's hundreds of millions or hundreds of billions, tens of thousands of billions even of these in many devices, including CPUs. Your memory is basically made up of these. Your volatile memory, being your RAM, and your computer, is made up of these. It's just a ton of these little electronic switches that can either be turned on or turned off. And so everything is basically comes down to a 1 or a 0. But starting off, let's just take a step back and let's talk about the numbering system that we use as humans on a pretty regular basis. Let's talk about base 10. We are going to count in decimal. All right, ready? Count with me. Just like kindergarten. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, etc. Now, when we go from 9 to 10, an interesting thing happens. We overflow from a single digit into a double digit. So once we exceed 9, we basically reset that ones place back to 0, and we carry over a 1 into the next decimal place. Now, we have, in 1 through 9 here, we just have a single digit, right? And then 10 through 13, we have 2 digits. But there could actually be, you can actually annotate these single digit numbers as 2-digit numbers and maintain their value simply by placing a 0 in front of them, right? So 0, 1 is the same as 1, and 0, 2 is the same as 2, and so on and so forth. So what's the furthest non-zero digit to the left is our significant digit, right? So whenever we overflow from 9 to 10, we're modifying that, and now 1 is our significant digit in the tens place here, and 0 is in the ones place. And we could throw a 0 in front of this number, in front of the 10, or in front of any of these two-digit numbers to make them 3-digit, and they would still maintain their same value. Hopefully most of this is you remember it from elementary school, right? So let's talk about the binary numbering system, and let's do some counting in binary. So 0, 1. Now there's only 2 possible values for this first digit, right? So as soon as we exceed 1, we move over to the next digit. So from 1 we go to 1, 0. Okay, and then we increment that ones place again. We go 1, 1. Now we overflow again from the ones place, and then we overflow from the twos place into the fours place. So we have 1, 0, 0 is this is 4, and then 1, 0, 1 is 5 in decimal, 1, 1, 0 is 6 in decimal, and so on and so forth. So it works the same way as counting in decimal. You start with the furthest right place when you increment the overall value by 1, and whenever you increment past a 1, you just overflow it to the next place. So again, just kind of converting each of these binary numbers to its decimal equivalent. We have 0, which is the same as 0 in decimal in any other numbering system. When we increment that, it goes to 1. When we increment that, it overflows into the twos place, and we get 1, 0. When we increment that, it's 1, 1. So that's we're now up to 0, 1, 2, 3. 4, when we overflow again into the fours place, 5, which is 4 and 1, 6, which is 4 and 2, 7, which is 4, 2, and 1, 8, 9, 10, 11, 12, 13, 14, 15, right? Now again, I just want to point out here significant digits. The same as in decimal, you can prefix any of these numbers with 1 or more extra zeros, and it doesn't change the value of the number, but it is kind of nice for purposes that we'll understand momentarily. So what I'm going to do here, I'm actually prefixing here so that we always have 4 digits, but like for these first couple, only this first place is significant, and for these ones, only the first 2 places are significant, right? So because it's all zeros leading up to the value, but 0, 0, 0, 1 is the same as 1. It's the same number, right? It has the same value. Just like in decimal, if you throw a 0 in front of 9 and you have 0, 9, it's still 9 as the value, right? All right, so now let's move on and talk about hexadecimal, which again is base 16. You have 16 distinct values per decimal place. So let's count in hexadecimal. Count with me. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. That's 15 unique values for the first decimal place. And then we overflow into the second one, and we have 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, A, 1, B, 1, C, 1, D, 1, E, 1, F. And again, we overflow the value then, and we're at 2, 0, 2, 1, 2, 2, and so on and so forth, until we get up to 9 in that 16th place. And then we have 9, 0, 9, 1, 9, 2, all the way up through 9F. And then when we overflow, that 9 increments to A, right? So it's the same as when we were doing single digit, just when we go from 9 to A, which is the next distinct value in hexadecimal, and then B, C, D, E, F. Same thing happens in the 16s place, and so on and so forth. So let's take a look at digit values and what each of these kind of digits actually represents. So I put together some tables here. So in our decimal numbering system, which again is what everyone's used to, you have the units place or ones place, right? And then you have the tens place, so values of 10. You have the hundreds place, values of 100. The thousands place, 10,000s, 100,000s, millions, 10 millions, 100 millions, so on and so forth, right? In binary, you have the units place, just like you do in decimal, but then because there's only two values for this, and then we flip over into the next place, that's the twos position. So anything in here is a value of 2. And then we have the fours position. And this is 2 to the n, because there are two distinct values for each position. However many places out you are 2 to that power for what that actually represents, right? So we've got units, 2s, 4s, 8s, 16s, 32s, 64s, 128s, 256s, 512s, and so on. So these numbers some of these numbers may stand out as being familiar if you've dealt with memory at all, or really anything computer-wise. If you've ever wondered why things are measured in values of 32s and 64s and 128s and 256s and so on and so forth up to 1024s, and then from there, the reasoning is because that's where everything lines up value-wise in terms of the digits in a binary number. And then same hexadecimal, we still start with units, but then this is 16 to the end. So we've got units, then 16s, then 256s, then 4096s, and so on and so forth, right? So that's what each digit in a decimal, binary, and hexadecimal number actually represents. So with the number, say, 9009, for example, we have 9 in the thousands place and 9 in the units place. Let's convert a binary number to a decimal number. So we're going to go with the binary number 100-10011. Okay, so we've got 1 in the units place, 1 in the 2's place, 0 in the 4's place, 0 in the 8's place, 1 in the 16's place, 0 in 32's, 0 in 64's, 0 in 128's. So how do we convert this to decimal? Well, all we have to do is add up those place values where we have a 1, where we have a value, we're taking that equivalent value. So what we end up doing is adding 128, which is our first one, plus 16, which is our second one, plus 2, which is our third one, plus 1, which is our fourth one, and we end up with 147. So 10010011 in binary is 147 in decimal, or vice versa. 147 in decimal is 10010011 in binary. And we're going to take a look at how that works when we do the other way around next. Okay, so now we're going to go the other way around. We're going to take a decimal number and convert it to binary. So let's use the decimal number 95. So whenever we convert a decimal number to binary, you basically have to do a little bit of sort of division and subtraction here. So we have to say, we'll start at the highest value, closest to this number, like the 128s, for example, on 95. 128 can't go into 95 because 95 is smaller than 128. So our 128's place is not going to have a value, it's going to be a 0. But 64 does go into 95, so that's going to be a 1. And then if we deduct that 64 from 95, we still have 31 as our remaining decimal value that we have to figure out how it fits into this. So does 32 go into 31? No, because 32 is larger than 31, so that's going to be a 0. Does 16 go into 31? It sure does, so that'll be a 1. We'll deduct 16 from 31 like we did before. Now we're down to 15 remaining. Does 8 go into 15? It does, so our 8's place is going to be a 1. We deduct 8 from 15. We still have 7 left over. Does 4 go into 7? Sure does. That's a 1. We deduct 4 from 7. We end up with 3. Does 2 go into 3? Obviously, yes. That's going to be a 1. Deduct 2 from 3, and we have 1. And, of course, that's our 1 left over for the units place. And so that's going to be a 1. And now we've taken this 95 and converted it in 95 in decimal and converted it into the binary number 01011111. The next conversion that I want to talk about is converting into hexadecimal. Now, we're not going to convert a decimal number directly into hexadecimal, but it's actually easier to convert binary to hex, hex being short for hexadecimal. And the reasoning for that is there's an interesting side effect of these being base 2 and base 16 numbers. For every 4 digits in a binary number, it is the same as 1 digit in hexadecimal, because hexadecimal overflows into a 16ths place, and 4 digits in, binary overflows into a 16ths place. Just an interesting kind of side effect of base 2 being something to the power of 2, base 16 being something to the power of 16. So for every 4 digits in a binary number, you have 1 equivalent digit in a hexadecimal number. And this is why, if you've probably heard the term byte, a byte is actually just 8 bits, being 8 zeros or ones, an 8-digit binary number, and each byte in each byte or 8 digits of binary is actually 2 digits of hexadecimal. So it's really really convenient that lines up in that way. Because that makes conversion really easy. Because if we look at 4 digits at a time, then we can convert that into a single hexadecimal digit, right? And we can do that, and everything's going to line up nicely. So yeah, that's converting binary to hex. Super easy because you're looking at 4 digits at a time. Now, I did mention that 4 digits is a byte. You may also, well, you probably have not heard of this, but 4 bits is referred to as a nibble, actually, in digital electronics and computing. So 4 digits is a nibble, 8 digits is a byte. Interesting stuff. So let's do a binary to hexadecimal conversion. I'm going to do a real simple one first. We have 1011 is our binary number, right? And we want to convert this into a hexadecimal number. So we know this is going to be a single hexadecimal digit already because it's 4 bits or 4 digits. So what value is it going to be? Well, 8 plus 2, which is A in hexadecimal, plus 1, which is B in hexadecimal. So 1011 in binary equals B in hexadecimal. Nice and simple, right? So let's look at a slightly larger value. Let's do a byte of binary. We'll do the number 11000011. Now I've broken this into 4-digit sections just to make it a little bit easier, because we know every 4 digits in binary is going to be 1 digit in hexadecimal. So we know that this 8-digit binary number is going to be a 2-digit hexadecimal number. So let's start with the first nibble here. We've got 8 plus 4, so that is 8, 9, A, B, C. So our first significant digit in hexadecimal is going to be a C. And over here, we have 2 and 1, so that's 3, which is 3 in hexadecimal. So the binary number 11000011 equals C3 in hexadecimal. Now, I already kind of explained why I'm covering binary, because that is sort of like really what's going on, like inside your computer. Anything that it's doing is basically just these strings of ones and zeros, right? And so if you can look at the binary, you can tell where things are at or what things are doing. You can really just break it down to really individual bits or switches and what's on and what's off, and that kind of determines what's happening inside of a system. But what about hexadecimal? Why am I covering that? Well, whenever you're dealing with significantly large numbers, like huge arrays of zeros and ones, and that's often the case when you're talking about either data or even addressing. There's so many of these switches in your RAM or in your memory that you need these big long addresses to tell the computer what memory you want to read from or write to. So so these addresses, these places in memory that you want to seek to and do things with, can be very, very large binary numbers. So with the hexadecimal and binary conversions back and forth being so easy, it makes a lot more sense to represent those addresses as hexadecimal values. Another place where you've probably seen hexadecimal is in CSS with color codes. So at this point, we have some more niceties in kind of newer iterations of the CSS standard, where you can do things like RGBA and things like that, and you can kind of define colors in different ways. You can call them out by name, but in the early days of HTML and CSS, the only real way to get kind of a custom color was to specify a hexadecimal color code. And the way that's set up is that you have 2 hexadecimal digits to represent red. So in decimal, that's a value between 0 and 255. Two digits for green, 2 digits for blue. So you end up with basically for each of those 3 base colors, you end up with 0 to 55 as values that specifies how much of that color is being included in your resultant color that you're trying to create. So hexadecimal, if you haven't seen it in CSS, you probably will stumble across it in Legacy at least somewhere else, and I still use hexadecimal to specify color codes all the time. So it's and even if you're using like RGBA, you're using decimal values, but you'll notice that those values for red, green, blue are 0 through 255 decimal values, and that's why, because it's actually a 2-digit hexadecimal number at the end of the day. All right, so we've talked about numbering systems, we've talked binary, we've talked hex, we've looked at converting back and forth between some of them, not all of them. I mean, obviously I didn't cover hexadecimal to binary, but it's the same concept, really. It's just the other way around. So like if we were converting C3 to a binary number, we would look at C and we would break it down kind of the same way that we did with our decimal conversion. We'd say the value of C is 8 plus 4. Or C minus 8 equals 4, 4 minus 4 equals 0. So we have 1, 1, 0, 0 as the value of C, and then looking at 3, 8 doesn't go into 3, 4 doesn't go into 3, 2 goes into 3 once, and we have 1 left over for our units. So 3 is 0, 0, 1, 1, right? So it's pretty common sense going the other way around, doing hexadecimal to binary versus binary to hexadecimal. A lot of times it's easier just to take a decimal number, convert it to binary first, and then convert it to hexadecimal, because you don't have those, you don't have to do hard math at that point. The binary conversion from decimal is pretty easy, as we saw, and the hexadecimal conversion from binary is super easy. And then same thing the other way around. If you want to know what a hexadecimal number is, it's generally easier to convert it into binary and then binary to decimal. There's just less math involved, and you can actually do a lot of it in your head if you're proficient with arithmetic. So